All right. Thank you, Killian, for the kind introduction. What an honor to be here today. I'm really I feel very privileged to be in front of this crowd. So today I'm going to talk a little bit about how I believe AI is transforming radiology. Um, and before I jump in, I'd just like to declare my sort of conflicts of interest. I advise two companies. One's a Cornell spin out. It's been about 10 years clearly, again, in the space of radiology and AI. Another one is a small startup at Cornell Tech right now called Medora. But first and foremost, I am an academic researcher. And I really do believe in open and transparent and ethically guided science in the space, and especially in public interest. And I really want to make that point today in my talk. So here's sort of a rough outline of the next 30 minutes or so. Initially, I'm going to talk a little bit about radiology, just to introduce what radiology is if you're not fully aware of it, and give a sort of a summary of what the state of affairs is in radiology today. And then I'll move on to sort of highlighting a couple of research threads that are ongoing in our research group at Cornell in this space, talking about very specific examples of how we develop AI for various radiology applications. And then I'd like to end on a rather speculative note that is a little bit grounded in our research, but also is supposed to predict the future in radiology, and I'll bound the horizon to 5 years, because anyone who tries to predict beyond 5 years, I think, is being a little silly. But first, I'm gonna start with a famous forecast that some of you might be familiar with, and this is about 10 years old now. As many of you probably in the room know, Jeff Hinton, who's at this point a Nobel laureate, Turing Prize winner, an AI, pioneer, made this very rather provocative statement in a conference in his hometown in Toronto about 10 years ago in the November of 2016, where he essentially claimed that we should stop training radiologists because essentially all the tasks that radiologists perform on a daily basis can be taught to an AI system, and a deep learning could essentially do that. And so his point was AI is essentially going to automate radiology and remove the humans from the loop. And the reality today is obviously not, this is not the case. And I'm going to sort of summarize where we are in terms of how AI is transforming radiology. But the point is that I think he was really wrong in his forecast. At least in terms of the timeline, it was wrong. Okay, so what is radiology? Well, radiology always starts with pixels. So you convert pixels, you first acquire these pixels, i.e. images. It could be an MRI scan, it could be a CT scan or an ultrasound or a PET image. And you convert these pixels into clinical decisions and insights. That's sort of the goal of the game. The MRI scan or the CT volume that you're acquiring, you start with that, and it's typically acquired in response to some clinical indication. And the goal of the game, again, is to reach a diagnosis or plan or guide a treatment, track disease progression, or assess an outcome of an intervention, right? So there's these sort of goals that we have in mind. And if you look at radiology today and the entire pipeline of radiology, much of it is already rather computational. So over the last 10 to 15 years or even longer, and throughout definitely my research career, we've been working on introducing algorithms in every step of the way, right? So anywhere from acquiring better images, faster images, presenting them in a way that makes more sense or are clinically more insightful, to enabling better interpretation downstream, to gaining population level insights. Every step of the way, computation or algorithms have played a role. In this new chapter or this new era that we're living through, obviously AI is the key player in this pipeline. Okay. Now, radiology is a hard problem. So on the right, I'm showing you a sort of an image of a typical radiology reading room. So if you go to any hospital, there's going to be a radiology reading room, at least one, if not more. And it's usually this dark room full of screens, and you have trained radiologists sitting in front of these screens, scrolling through these pictures. These are your pictures that have been acquired like an MRI scan. And as they're scrolling through these pictures, they're obviously looking for issues in the anatomy, the various structures, various lesions, and they have a dictation device that they're talking into, which basically transcribes the report, the radiology report. That's the end product of that reading session. Usually you have a few minutes, 5 to 15, 20 minutes at most to read an entire study. Uh, High stakes problem, as you can imagine. You don't want to get the diagnosis wrong. You don't want to miss anything. It's done under time pressure. Obviously, the patient's health is on the line. There's a lot of very intrinsic uncertainty. So there's a lot of risk and a lot of trade-offs that need to be made. And there's obviously legal liability that we need to be concerned about. Now, if you look at sort of the radiology workload across the globe today, we are getting a very rapidly increasing number of scans. So the number of pixels or the number of images that we're acquiring are growing very fast, exponentially fast. We're imaging more patients. Patients are getting more images. And we know more about these patients, so the read or the interpretation of these images is getting more complex. And despite all this increasing complexity and demand, we're not training more radiologists. So the common example I like to give is if you look at the residency program at Cornell, the radiology residency program from the year 2000 till today went from 9 residents a year to 10 residents a year. So our growth was less than 10%. Or about 10%. Whereas if you look at like engineering PhD programs, we've tripled or quadrupled in some of these programs. Right? So there's a big difference in terms of the need and how many radiologists we're training. Now, the other thing that I'd like to emphasize is we have a huge data bottleneck problem in radiology. So as I sort of alluded a few slides ago, if you look at a typical radiology study, an MRI study, it will contain hundreds of thousands, if not millions of pixels. All of those pixels get interpreted typically by a human expert, sometimes with assistance using, let's say, AI tools, that then converts all of that information into a report that is usually 2 pages long. And so that report, as you can imagine, misses a lot of information. We're leaving a lot of information on the table. As I will sort of briefly demonstrate in a few slides, these reports are usually very narrative, they're subjective. They can have a lot of mistakes in them, actually, unfortunately. They will miss some important things in these scans. And rarely will they have any quantitative measurements. And that's something that we'd like to sort of improve. And so to me, this is where AI has the biggest opportunity in the next 5 years, is to improve the state of affairs in radiology. Okay, so I'd like to make this a little concrete. So I'm going to start with basically highlighting a couple research areas that are areas that we've been working on. The first one is a clinical condition that's called autosomal dominant polycystic kidney disease, or ADPKD. As the name implies, it's an inherited disease. It's actually quite common. And what happens in ADPKD is patients in around, in their 50s or 60s start developing cysts, typically starting in their kidneys, often spreading beyond the kidneys into, say, the liver. These cysts by themselves are actually benign, but they proliferate and grow, and they crowd out internal organs. And that's the main issue you're dealing with. If left untreated, this condition would lead to an end-stage kidney disease, renal failure. Progression, though, varies wildly across patients. So certain patients are very stable over decades, and others progress very rapidly. And in imaging, in fact, longitudinal imaging, so imaging over time, is an important tool for us in the clinical management of these patients. So if an ADPKD patient, if they're lucky, they would get an annual scan. Usually they get it every 1 to 3 years, but if they're lucky, they get it annually. And that scan would be a multi-sequence MRI scan, which I'll describe in a second. And the goal of this MRI study is to assess disease burden. So how far along in the disease are you? How many cysts you might have in your kidneys? quantify the rate of progression over time, right? So when they're getting these annually, how much things have changed since their last scans. If they're on a treatment, and I'm going to mention one specific treatment in a second, evaluate whether they're responding to that treatment or not, and obviously screen for other issues like aneurysms or infections. Now, this is what one specific volume of an MRI sequence will look like. Now, when you go in and get an MRI study, you don't get just one picture. You get a three-dimensional volume, so it slices, multiple slices. And often you have multiple volumes like these because each type of you can actually program an MRI scanner to highlight various aspects of physiology and anatomy. We call these sequences. So you might have multiple sequences in an MRI study. I'm going to visualize a single sequence. It's a T2 weighted sequence, so it has a very specific contrast where the fluids will appear bright, and the fluid is basically highlighting where the cyst is in the ADP kidney. This is the abdomen of a patient, and you're sort of going from front to back as the images are scrolling. And this is what a typical radiologist would see, right? So they're scrolling through the abdomen, and they see all the internal organs, and they see the kidneys full of cysts, and they sort of try to quantify how much the disease has progressed and maybe changed from their last scan. Obviously, reading these images is not trivial, right? People's anatomy varies quite a bit. And comparing to prior scans is not an easy exercise either, right? So you have to sort of establish the correspondence and really pay a lot of attention to figure out what the real change is in these scans. Okay, so all that complexity, and as I said, there's hundreds of thousands, if not millions of pixels in those images in a single MRI study, gets essentially distilled into a report that will look like this. This is a snippet of a report. It's usually, as I said, a couple pages long. And it's sort of, it does reflect the clinician's expertise, radiologist's expertise, but is often very causative, and it will be very descriptive. It will describe the cyst and what the enlargement looks like, but it will not give very precise measurements. Sort of an exception is in polycystic kidney disease, the size of the kidney, the total kidney volume, is what matters a lot for the treatment and management of these patients. So there will typically be an attempt at quantifying that size. So for instance, there might be a single linear measurement from the sort of largest cross-sectional area, or a more sophisticated version of that, which I'll talk about in a second. But beyond that, there will be these subjective narrative statements that are sort of pointing out the clinically significant findings in the image. Now, as I mentioned, total kidney volume is an important metric. So we want to measure the kidneys in this disease, and we want to measure them as precisely as possible. And as I said, in a typical MRI study, we'll have different contrasts and different views, right? So we might have a front-to-back view, which we might call coronal view, or a side-to-side view, or top-to-bottom view, or an axial view. And we might have T2 weighted images or different types of contrast, like an SSP or a T1 weighted image. Now, each one of these views and contrasts will give us the opportunity to measure total kidney volume in a sort of an independent way, right? So we can measure in each one of these both the left and the right kidneys one by one, and then maybe take an average to get a robust estimate of the kidney volume in that patient at that given time point. Now, that we might imagine is going to be a tedious task, right? So the standard or the gold standard radiological interpretation of total kidney volume essentially involves this simple geometric approximation that relies on three linear measurements. So you find the length, the width, and the height of the kidney and just use a simple formula, assuming it's like an ellipsoidal approximation, and that's your estimate for a kidney volume in that image. Obviously, that's not going to be precise. That usually has around an error rate around 10%, and that's definitely not precise enough to be able to track longitudinal progression. And you can do a much better job if you sort of delineated the contours more precisely, and you can imagine that's going to be time-consuming. In fact, it takes about 9.5 to 10 minutes per image sequence per kidney to do that. So if you had, say, 6 sequences or 5 sequences, and you have 2 kidneys, that's going to be over a couple of hours actually of time to really measure the kidneys' volumes. which gives you the precision we want, but obviously is not a scalable exercise. So this is, first I need to emphasize why total kidney volume is important. For the clinical management of these patients, total kidney volume is the quantitative biomarker. The change in kidney volume over time gives a way of classifying these patients clinically and allows us to prescribe medication to these patients. So there's a specific medication called tolvaptan, and tolvaptan is the only medication that's actually FDA approved for these patients. It costs about $200,000 a year per patient, and it's only effective in about half of these patients. In the other half of the patients, it's not effective and can lead to a lot of side effects as well. So the way you sort of assess whether this patient is responding to this therapy or not is to see if their kidney growth has slowed down over time. All right, so measuring kidney volume is extremely important in these patients. So what we saw when we were approached by our clinical collaborator about 3 years ago at this point, this is Martin Prince, who's a radiologist colleague of mine at Cornell. I saw this as an immediate opportunity where AI could make a big difference. It's segmenting objects and measuring precisely about volumes of objects in an image is a rather straightforward problem in AI or in computer vision. So that's essentially what we did. We essentially started this collaboration to focus on how do we develop this tool, this AI segmentation tool, deploy it and validate it. And the goal here is to essentially get a tool that will be precise enough and allow really the clinical mismanagement of these patients. We had this human in the loop paradigm where essentially we had some data where radiologist experts spend the 2 hours needed to annotate those pixels from scratch without any assistance. We created a curated database from using that effort, and then trained an AI model on that database to automate that. Obviously, that first version of the AI model was not perfect; it made errors. But in the second generation, we did not have humans annotate from scratch. All they did was review and correct those automatic segmentations, and we sort of implemented this over multiple generations until we got a very reliable, robust model. We still have a human in the loop who inspects all our results. By the way, I need to preface to say that this is all clinically deployed today at Cornell. And the human experts in the loop are just essentially reviewing and accepting the automatic segmentations at this stage for the kidneys. Now, thanks to this sort of workflow that we've implemented, we can essentially obtain very precise measurements of kidney volume within minutes per study, which allows us to endow the narrative radiology report that we are generating in our workflow with a quantitative table of kidney volumes and actually other things that I'm going to talk a little bit about in a second. But the important point here is that these volume measurements that we're getting are extremely precise. Our error is around 1 to 2%, which enables us to actually assess whether a patient is responding to tolvaptan therapy within less than a year. So in the old paradigm, where we had these sort of crude approximations for total kidney volume, it took us 3 to 4 years to be able to figure out whether a patient was responding to this treatment or not. I want to remind you 2 facts. One is half of the patients don't respond to this treatment, and the second fact is it costs about $200,000 per patient for this treatment. Okay. So this is what these segmentations look like. We have very detailed sort of masks that represent the right and left kidney and gives us these very precise measurements of total kidney volume. And we can do this on every single MRI sequence. So we have, say, the coronal, this would be the axial stack. That would be the coronal stack. So remember, in an MRI study, we will have multiple sequences. And so we can measure the kidney volume in each one of these sequences. In a given MRI study, these volumes should be exactly the same. So you can imagine that these are independent measurements of the same thing. You can do some sort of simple statistics on these measurements to be able to get a much more robust and accurate measurement. And that's what we do. And we can plot these measurements over time for a given patient. Remember that these patients are coming through our clinics once a year or every couple of years. And as they do, we can measure their total kidney volume. And in each dot in this plot represents a different sequence, and the average would be the best, most robust, or most precise estimate we get for that patient at that time point. And we can see how the total kidney volume will evolve over time. And for this particular patient, we can see also how tolvaptan slowed down the progression of the disease when they were introduced to the therapy around the age of 40. Now, I talked a lot about how we can measure total kidney volume, but as you might have appreciated as you look through the abdominal MRI study, the abdomen contains much more than kidneys, right? We have the entire GI tract in there. We have our liver in there. We have fat. We have muscle. We have the cerebro in there. So what we can do is we can segment out all these different structures and anatomies, right? So, and it's really from a technical standpoint not that hard. We can implement exactly what we did before, but with this human in the loop paradigm, and develop models that can essentially quantify all these different anatomical structures in an abdominal MRI study, which essentially allows us to produce now really rich quantitative tables for every single MRI study that we are acquiring in the clinic. To me, this is where the exciting work begins, because if you think about it, now we can measure all these different things in an MRI study. The question then becomes, how do we interpret these measurements? What is the clinical significance of these measurements? How do we present these measurements to patients or providers? Do we go beyond, say, PKD or a specific disease into, say, wellness or metabolic health or aging or opportunistic screening, which I'm going to allude to at the end of my talk. Okay. Now, I'd like to go down a second thread more quickly, I guess, since I'm running out of time. The PKD example was measuring anatomy in a given MRI study, and we would look at the trends over time in this MRI study, in this measurement that we're extracting. But much of medicine is really trying to understand what's changing over time in very subtle ways on things that we don't maybe expect. And so the question is, can we develop an AI framework that actually discovers reliably what is changing over time in longitudinal imaging? And so this is a common problem that we face. So you have, say, in the context of aging, in the context of treatment response, in the context of development or disease progression, you would have the same patient scanned over time, over years, many, many times. And you always have the same question: what is changing over these many years and what's clinically significant? So this is so the longitudinal change question is a common theme in radiology. And you can imagine that, maybe you can appreciate as you're looking at these images that are longitudinal, that the change is going to be very subtle and very localized often and hard to detect for humans, right? So you have to sort of do a really detailed comparison, which is time consuming and tedious. So we were sort of very intrigued by this question, and essentially there's two things that you want to do. You want to first understand at the population level what is changing commonly across individuals, like in Alzheimer's disease, what's happening to these patients' brains. And you also want to, at the individual patient level, to be able to pinpoint and quantify what is changing as well. So there's two types of questions you're interested in. And in answering those questions, you're always dealing with this issue of, there are things that change from scan to scan that are uninteresting. You might be using a different scanner. You might, the patient might be positioned differently in the scanner. There might be noise and artifacts. So the question is always, how do I disentangle those uninteresting variations from what I think is the clinically interesting or significant one? So the way we approach this, it's based on a very simple technical idea that I just want to briefly describe. And it's really, I think, hopefully, I can convey the idea using this very simple example. So I often like to, when we're talking about computer vision type problems, I often like to think of faces, human faces, because I think the human visual system we all know is very good at understanding human faces, recognizing them and recognizing various patterns in human faces. So it's a good sort of working example for me. So if you looked at this sort of series of images of the same human face over the course of their lifetime, and you might all recognize that this is an AI generated set of images. The reason it is AI generated is I just wanted to make sure that the images look very uniform. You don't see differences in like the pixelation or the quality of the image. I think everyone in this room will be able to recognize which of the images would be from the older person versus the younger person, right? So if I gave you two images at random, you could time order these images easily, because we all know how to sort of figure out or pick up on the sort of cues of aging, right? So we know that the wrinkling effects in the face and the sort of the graying of the hair and so on and so forth. So to me, this was our hint at training it. How do we train an AI system to pick up on change over time? And the way we did that was we basically taught an AI system to learn the arrow of time in longitudinal imaging. By that, what I mean is we basically taught an AI system to time order longitudinal images. So if I gave the AI system randomly ordered images that were required at different time points and asked the question of which one came first, if it could reliably answer that question, it had basically figured out what changes consistently over time, and it was able to localize and quantitate that. And so we applied this idea to a range of applications, including in the context of Alzheimer's disease and aging that we highlighted in a PNAS paper last year. So that's sort of the second point that I want to talk about in terms of the works that we're focused on these days. But what I'd like to do right now in the last couple of minutes is just take a step back and talk about where radiology, I think, is going. I know I started this talk with Jeff's famous prediction that we should basically stop training radiologists. It was a provocative statement, as I mentioned, but it was largely wrong. And this is a lesson I constantly remind myself. I think we should all stop making big predictions about the future, I guess, and be a little bit more humble, but especially about areas that we're not domain experts on. But I'm still gonna try to look ahead a little bit in radiology. Okay, so what I feel confident about where radiology is headed with AI is AI will not make radiology smaller. I think it's going to expand radiology. It's going to make it a broader discipline. It's going to give us better scans, more value per scan. It's going to give us new workflows. It's going to enable us to do faster, cheaper, lower dose and higher resolution imaging. Give us more measurements, more quantitative risks, and more ability to longitudinal track. And I think what's going to happen is AI is going to help radiologists keep on top of all this information, right? So that's gonna be a key. Now, scans are today typically obtained in response to a clinical indication, right? So you have some clinical indication and you would order a test. I think there's two societal trends that are happening that's important to highlight right now. That's changing this picture. First, scanning is becoming more affordable and accessible. So patients are getting more scans and they're getting scans to, say, monitor their health. So wellness checks, like whole body MRIs, are becoming a thing now. And in this new era, patients are demanding more out of those pixels than they used to. So it's not just to get to a diagnosis, but they want a richer information extracted from those pixels. I think opportunistic screening is a new paradigm that I'm very excited about that AI is enabling. So if you think about the sort of the old school of doing things, you would get a chest CT or a non-contrast chest CT for, say, lung cancer screening. But obviously, the chest CT contains much more information. So we can develop AI tools that can scour those pixels for things like evaluating bone health or cardiovascular health or metabolic health. Okay, and the final point I want to make actually is, all right, I know I'm out of time. So I want to make the final point is actually really important to me. So the next phase of AI, I think, is not going to be determined by who has the largest model, who has the most accurate model. I think the hard work is really in clinical translation and deciding what should we measure and how we should report these measures and what should be triggered as follow-up. And we should always focus on avoiding bias and over and under diagnosis. And I think places like Cornell and academic institutions in general have a unique role in all of this, because this is where engineering radiology, clinical medicine, data, ethics, and education all come together. And I think this is where we can actually build AI tools that are evidence-based and can be integrated in the real world so that it will have the impact on our patients. All right, I'll end there. Thank you.